Just yesterday, the James Webb Space Telescope, JWST, completed its final deployment sequence, marking the beginning of a groundbreaking era in space exploration. This incredible piece of technology has allowed humanity to peer deeper into the cosmos than ever before. However, with this leap into the unknown, we may have encountered something even more mysterious than galaxies and nebulae. Recent data from JWST hints at an extraordinary phenomenon, a set of unusual lights on a distant planet, Proxima Centauri b. This planet lies around 7 trillion miles from Earth, and this discovery rekindles age-old questions about the possibility of intelligent life beyond our solar system. The discovery of these lights has sparked both scientific curiosity and public speculation. Could this be the first evidence of an alien civilization, or might there be a sophisticated natural explanation? To unravel this mystery, we must delve deeper into JWST's extraordinary capabilities, explore its findings on Proxima Centauri b, and consider how this discovery might redefine humanity's understanding of life in the cosmos. The James Webb Space Telescope represents a significant advancement in astronomical technology. Designed to observe the universe in the infrared spectrum, it marks a considerable leap beyond its predecessor, the Hubble Space Telescope, which focused mainly on visible light. JWST's infrared capabilities are particularly crucial, as infrared wavelengths can penetrate cosmic dust clouds that block visible light, allowing clearer views of distant galaxies, exoplanets, and the earliest stars. This capability is especially beneficial for studying planets like Proxima Centauri b in remarkable detail. Proxima Centauri b orbits within the habitable zone of its host star, Proxima Centauri, the closest star to our solar system. The habitable zone is a region where conditions may allow liquid water to exist on a planet's surface. Proxima Centauri b is situated approximately 4.7 million miles from its star, potentially maintaining temperatures conducive to liquid water, a critical ingredient for life as we know it. Observing Proxima Centauri b through infrared detection, particularly on the planet's night side, is essential because it enables astronomers to detect faint heat signatures or thermal emissions that could provide insights into atmospheric composition or surface phenomena. JWST's capacity to capture such fine details makes it an invaluable tool for searching for potential signs of extraterrestrial life or for atmospheric conditions that might support it. The telescope's advanced instruments, such as the near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, supply highly sensitive spectroscopic data that are essential for identifying gases like methane and carbon dioxide in exoplanet atmospheres. These gases are considered potential biosignatures, as their presence in specific ratios could suggest biological processes. This capability is particularly relevant for Proxima Centauri b, where the discovery of unusual lights on the night side has stirred curiosity about whether these lights might result from artificial or natural phenomena. JWST's infrared capacity even surpasses some of the planned ground-based extremely large telescopes, ELTs, in certain ways. While ground-based ELTs, like the upcoming European Extremely Large Telescope, ELT, aim to capture direct images of exoplanets, their instruments are hindered by Earth's atmospheric interference. In contrast, JWST operates from space, free from atmospheric distortion, enabling it to capture clearer and more detailed data. Together, these ground-based and space telescopes complement each other in the quest to understand distant worlds. JWST's infrared technology currently offers a unique edge for planetary observations, including those of Proxima Centauri b. These advancements not only refine our understanding of Proxima Centauri b but also pave the way for future exploration of more distant planetary systems and potentially habitable exoplanets. By probing deeper into the infrared spectrum, JWST enhances our knowledge of planetary atmospheric conditions, surface temperatures, and possible biological markers, offering humanity unprecedented insight into alien worlds and the prospect of life beyond Earth. Proxima Centauri b is an exoplanet orbiting Proxima Centauri, the closest star to our solar system, located approximately 4.24 light-years away. With a minimum mass about 1.3 times that of Earth, Proxima Centauri b lies within its star's habitable zone, where conditions may allow for liquid water on its surface. However, the planet is exposed to significantly higher levels of high-energy radiation than Earth, including 30 times more extreme ultraviolet radiation and 250 times more X-rays. This intense radiation presents challenges for atmospheric retention, crucial for sustaining life. Studies suggest Proxima Centauri b could lose a substantial portion of its atmosphere relatively quickly due to the high levels of stellar activity from Proxima Centauri. Under certain conditions, it could lose an amount equivalent to Earth's entire atmosphere in as little as 100 million years. The planet's orbital characteristics further influence its potential habitability. Proxima Centauri b is likely tidally locked, meaning one side always faces the star while the other side remains in darkness. This alignment could create extreme temperature differences between its day and night sides, depending on whether it possesses a substantial atmosphere to moderate these variations. Additionally, Proxima Centauri b's evolutionary history is intriguing. It likely spent considerable time outside the habitable zone during its early formation, potentially impacting its water reserves and overall habitability. The initial water delivery conditions during the planet's formation remain uncertain, making it difficult to gauge its current potential to support life. Recent observations by the James Webb Space Telescope have detected strange lights on Proxima Centauri b, leading to speculation about their origins. Whether these lights are natural phenomena or indications of extraterrestrial life remains unknown, but the telescope's ability to capture infrared emissions provides valuable insights into the planet's atmospheric composition and thermal characteristics. Proxima Centauri b, orbiting our closest stellar neighbor, has long been intriguing because of its location within the habitable zone, which suggests it could potentially support liquid water. However, JWST's recent observations have unveiled something even more enigmatic: unusual flickering lights on the planet's dark side, prompting intense scientific curiosity and speculation. These lights, unlike anything observed on other exoplanets, seem to originate from the planet itself rather than from solar flares emitted by its parent star, Proxima Centauri. The flickering appears steady yet intermittent, suggesting multiple theories about its origin. One plausible theory is that the lights could be due to geological activity, such as volcanic eruptions. If Proxima Centauri b has active volcanoes, molten lava might emit light, creating the flickering pattern detected by JWST. Another natural explanation could be auroras, similar to Earth's northern lights, caused by interactions between a planet's atmosphere, if it has one, and the intense solar radiation from Proxima Centauri, a highly active red dwarf star. Yet the most tantalizing theory posits that these lights might be of artificial origin, potentially signaling the presence of an advanced civilization. Some scientists suggest that the lights could result from large-scale energy use, perhaps from cities or other infrastructure. Although purely speculative, this raises the exciting possibility that Proxima Centauri b could harbor intelligent life. Other explanations include the possibility of reflective surfaces on the planet, like ice or water, which could scatter light from the star in erratic patterns. Such reflections might account for the flickering observed by JWST. Scientists are eager to collect additional data to solve this mystery. JWST will continue to monitor Proxima Centauri b, and other observatories are expected to participate in further studies of the planet. By analyzing different wavelengths of light and conducting follow-up observations, astronomers hope to identify the exact cause of these strange lights. Potential future missions, like the Breakthrough Starshot project, could even send probes to the Alpha Centauri system for a closer look at Proxima Centauri b. The city-like lights observed on Proxima Centauri b by JWST have drawn significant attention, as they resemble the glow of city lights on Earth. The recent discovery of unusual lights on Proxima b has sparked speculation about potential signs of extraterrestrial civilization. The possibility of artificial lights on this distant exoplanet is an intriguing hypothesis, though scientists remain cautious in their interpretations. These lights could have alternative explanations, including natural geothermal emissions or auroras resulting from interactions between solar particles and the planet's atmosphere. A primary hypothesis proposes that the lights might indeed signal an advanced technological civilization. If verified, this discovery would mark the first direct evidence of extraterrestrial technology, significantly altering our understanding of life beyond Earth. The organized light patterns observed suggest a level of sophistication generally associated with developed societies capable of manipulating their environment to create vast illuminated structures. Yet, other theories propose that the lights could be the result of unique natural phenomena on Proxima b. Given the planet's orbit around a red dwarf star, Proxima Centauri, known for frequent stellar activity and solar flares, These flares could create unusual atmospheric effects or geological processes that produce light emissions mimicking artificial illumination. Alternatively, the lights might stem from energy production methods unfamiliar to Earth, such as a civilization on Proxima b harnessing energy from its star or using unconventional sources. This could involve advanced techniques, like antimatter reactors or other exotic energy forms, that are beyond our current understanding. Proxima b, just over 4 light-years away, orbits within the habitable zone of its red dwarf star, where liquid water might exist. However, the planet experiences intense radiation from its star, posing a challenge for atmospheric retention and any potential life forms. Despite these challenges, Proxima b's proximity to Earth and the capabilities of the James Webb Space Telescope, JWST, make it an ideal candidate for further study, particularly in analyzing its atmospheric composition and surface conditions. The JWST's ability to detect infrared light is crucial, as it allows for the observation of thermal emissions from the planet, even on its night side, where these mysterious lights were initially detected. These emissions could be the result of volcanic activity or other heat sources, though the resemblance to artificial city lights cannot be fully dismissed without additional data. Scientists note that for these lights to represent evidence of intelligent life, they would need to have been consistently visible over thousands of years, awaiting detection by advanced human technology. Tidal locking likely affects Proxima b's climate and habitability due to its close orbit around Proxima Centauri. This phenomenon keeps one side of the planet in perpetual daylight while the other remains in darkness, creating a severe temperature contrast. Such conditions form what is known as an eyeball planet, where extreme climate zones exist. The narrow, terminator zone, between the day and night sides might be moderate enough to support life, allowing the presence of liquid water essential for life as we know it. However, the habitability of this zone depends on factors like atmospheric composition and heat circulation. A thick atmosphere could redistribute heat, making the terminator zone more temperate. Without such an atmosphere, the stark temperature differences across the two hemispheres would make sustaining life challenging. Another significant challenge for Proxima b is atmospheric erosion. Due to its proximity to its host star, the planet endures intense stellar winds and radiation, which can gradually strip away its atmosphere. Red dwarf stars like Proxima Centauri are known for their frequent, powerful flares, which could exacerbate atmospheric loss. If Proxima b has already lost its atmosphere, its surface would be hostile to life due to exposure to ultraviolet and X-ray radiation. Conversely, if it retains an atmosphere, it could shield the surface from radiation and stabilize conditions within the twilight zone. Researchers have proposed various models to understand Proxima b's climate dynamics. One study suggests that oceanic ice may drift into warmer regions, potentially leading to global freezing. Conversely, other models predict that warm ocean currents could transport heat to the night side, melting ice and creating a more temperate global climate. This uncertainty highlights the complexity of Proxima b's potential habitability. Tidal locking's unique climate conditions may also impact geological activity. If Proxima b has a molten core and experiences tidal heating, it could sustain volcanic activity that might replenish its atmosphere over time, creating conditions conducive to life by cycling nutrients and maintaining a more stable environment. However, the light emitted by Proxima Centauri is skewed toward the infrared spectrum, rather than visible light, posing challenges for photosynthesis as we know it. This means that any life forms on Proxima b would likely need to adapt to biochemical pathways different from those on Earth. The JWST and other instruments are continuing to observe Proxima b's thermal emissions and atmospheric properties, providing valuable data to assess the planet's potential to host life. Detecting greenhouse gases or atmospheric markers could reveal insights into Proxima b's climate regulation mechanisms. The study of Proxima b and similar exoplanets has grown more sophisticated with spectroscopy, a technique central to the search for biosignatures. The JWST is exceptionally capable in exoplanetary studies, particularly in identifying biosignatures on planets like Proxima b. By analyzing how specific molecules in an exoplanet's atmosphere absorb different wavelengths of light, the JWST reveals chemical compositions. For planets orbiting M-dwarf stars, like Proxima b, finding gases such as oxygen and methane is significant, as their presence together could indicate biological processes similar to those on Earth. However, the JWST's sensitivity to atmospheric composition varies depending on these elements' presence and atmospheric density. Detecting oxygen alone is challenging without substantial exposure time, yet the simultaneous presence of methane and oxygen may signal biological processes, as these gases typically neutralize each other over time without a replenishing source like photosynthetic organisms. Another potential biosignature the JWST can identify is a disequilibrium between methane and carbon dioxide. Such an imbalance might imply life, as geological processes typically produce these gases in equilibrium. Research on the JWST's capacity to detect biosignatures has shown promising results for exoplanets around red dwarf stars, including Proxima b. Future observatories like the Extremely Large Telescope, ELT, are expected to complement the JWST's capabilities, enhancing sensitivity for gases like methane and oxygen through direct imaging techniques that block starlight, allowing for more precise atmospheric analyses. Discovering biosignatures is complex, with technical challenges and long observation times required. Nevertheless, the JWST's advanced infrared spectrometers are currently the most powerful tools for such missions, enabling scientists to narrow down potentially habitable planets and detect essential chemical indicators that could signal extraterrestrial life. This leap in identifying habitable planets underscores the JWST's role in advancing astrobiology and our understanding of life beyond Earth. Proxima Centauri b is a hostile but potentially habitable world, presenting both exciting possibilities and formidable challenges for sustaining life. Located in the habitable zone of Proxima Centauri, the planet sits close enough to its star for liquid water to potentially exist, though this positioning also exposes Proxima b to intense stellar activity. Red dwarfs like Proxima Centauri frequently emit powerful flares that release large amounts of ultraviolet and X-ray radiation, which can erode planetary atmospheres over time. For Proxima b, this exposure means its atmosphere may deplete at a rate up to 10,000 times faster than on Earth, with high-energy particles ionizing atmospheric gases, allowing them to escape more easily into space. This process, exacerbated by temperature fluctuations in Proxima b's thermosphere, makes it difficult for the planet to retain essential gases for life, such as oxygen and nitrogen. To mitigate these atmospheric losses, Proxima b would require either a strong magnetic field or a dense protective atmosphere. Earth's magnetic field shields its atmosphere from solar winds, reducing the stripping effects of solar radiation. However, due to Proxima b's proximity to its host star, the planet may require an even stronger magnetic field or a thicker atmosphere to offer comparable protection. Studies involving magnetic simulations suggest that without these defenses, Proxima b would struggle to maintain an atmosphere conducive to life as we understand it. Yet, if Proxima b has adapted to its extreme conditions, it might demonstrate resilience similar to extremophiles on Earth, organisms that thrive in harsh environments, such as acidic springs or deep-sea hydrothermal vents. One significant concern regarding Proxima Centauri b's habitability is its proximity to its host star. The planet orbits at a distance of only about 1/12 of the distance between Earth and the Sun, completing a full orbit in just 11.2 days. This close orbit likely causes tidal locking, leaving one side of Proxima b constantly facing the star while the other remains in darkness. Such a configuration could lead to extreme temperatures on both sides, with a narrow region along the terminator, where day meets night, offering more moderate conditions potentially suitable for life. The host star's intense stellar activity, including frequent flares and high radiation levels, poses further threats to any atmosphere Proxima b might retain. Studies indicate that ultraviolet and X-ray radiation from Proxima Centauri could strip away an Earth-like atmosphere in a few 100 million years, potentially leaving the surface exposed to harmful stellar radiation. Without a protective atmosphere, surface conditions would be inhospitable for life as we know it. If Proxima b does possess an atmosphere, it may not remain stable over the long term due to the constant barrage of radiation and stellar wind from its host star. The magnetic field of Proxima Centauri b is also uncertain. Without sufficient magnetic protection, its atmosphere would be even more vulnerable to erosion. To explore these possibilities, scientists plan to use the James Webb Space Telescope, JWST. This telescope's advanced spectrometers can analyze Proxima b's atmosphere by examining how it absorbs and reflects different wavelengths of light. By observing spectral signatures, JWST could detect gases like oxygen and methane, which, if found together, might hint at biological processes. Continuous monitoring by JWST will allow scientists to evaluate Proxima B's atmospheric stability and resilience to Proxima Centauri's intense space weather. Should future observations reveal an atmosphere capable of withstanding this radiation, Proxima b could serve as a unique model for studying habitability under extreme conditions. The TRAPPIST-1 system presents another exciting target for the JWST, with its 7 Earth-sized exoplanets, 3 of which, TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f, fall within the habitable zone of their cool red dwarf star. This arrangement makes them potential candidates for liquid water on their surfaces. JWST's advanced spectroscopic capabilities allow it to analyze these planets' atmospheres through transmission spectroscopy, where starlight passing through a planet's atmosphere reveals specific molecular signatures. Scientists are especially interested in detecting potential biosignatures, such as oxygen, methane, or carbon dioxide, which might indicate life-supporting conditions. However, TRAPPIST-1's status as an active red dwarf adds complexity to these analyses. The star's flares and intense activity can produce misleading spectral signals, complicating the identification of atmospheric gases. For instance, observations of TRAPPIST-1b suggest the planet lacks a thick hydrogen atmosphere, and some spectral readings may reflect stellar influences rather than the planet's own atmosphere. TRAPPIST-1's stellar variability adds further challenges. Stellar faculae and spots can obscure or mimic the absorption lines scientists use to detect atmospheric gases, adding a layer of complexity to data interpretation. Researchers work around this issue by using models to subtract stellar noise, though this remains challenging, particularly for close-orbiting planets like those in the TRAPPIST-1 system. The planets in this system are tightly packed, with orbits confined within a region smaller than the distance between the Sun and Mercury. This proximity creates dynamic gravitational interactions and complex orbital resonances, particularly among the inner planets, that challenge traditional models of planetary formation. These resonances likely stem from the planet's formation in a protoplanetary disk, with their current configurations providing valuable insights into planetary system evolution. Future studies on TRAPPIST-1's habitable zone planets, TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f, will be crucial for gaining more detailed knowledge of their atmospheric compositions. These planets are thought to have lower exposure to stellar radiation, potentially increasing their ability to retain atmospheres. Ongoing analysis and modeling aim to refine techniques for managing stellar contamination, essential for accurately characterizing the atmospheres of planets in TRAPPIST-1's habitable zone and assessing their potential for supporting life. The future of exoplanet exploration holds immense promise, with the James Webb Space Telescope, JWST, at the forefront of studying distant worlds. However, upcoming telescopes like the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope are expected to greatly expand our ability to identify and analyze potentially habitable planets. The ELT, anticipated to start operations by 2028, will feature a primary mirror nearly 40 meters across, delivering about 16 times more clarity than the Hubble Space Telescope. This advanced resolution will allow it to capture faint signatures from distant planets, enhancing the detection of potential biosignatures such as water vapor, methane, and oxygen, all while counteracting atmospheric distortion through adaptive optics. Such high levels of detail will enable astronomers to determine if distant worlds possess atmospheres suitable for life, especially in red dwarf systems known for high radiation activity, like Proxima b and the TRAPPIST-1 system. Following the achievements of JWST, future missions such as the European Space Agency's Ariel and NASA's Nancy Grace Roman Space Telescope are set to further expand our capabilities. Ariel, scheduled for launch in 2029, aims to perform a comprehensive survey of exoplanet atmospheres across a wide range of planets, focusing on their chemical compositions and potential for habitability. Meanwhile, the Roman Space Telescope will be equipped with a coronagraph instrument that blocks out light from host stars, allowing direct imaging of exoplanets that would otherwise be obscured by stellar glare. This technology is expected to significantly improve our ability to observe Earth-like planets and study their atmospheres for signs of habitability. The exploration of oceans on exoplanets represents another critical focus area for future telescopes. Astronomers are developing techniques to detect subtle changes in a planet's reflectivity as it rotates, revealing surface features such as oceans or land masses. The ability to identify water, a fundamental ingredient for life, on distant worlds will be vital in the search for extraterrestrial life. As these next-generation instruments come online, the focus will shift from simply discovering exoplanets to characterizing them in detail, including the identification of atmospheric patterns that could indicate biological versus geological processes. Integrating advanced optics and spectrometric techniques will allow scientists to analyze faint light reflected from these planets, providing insights into their potential for supporting life. With this collaborative approach, astronomers hope that these upcoming observatories will yield groundbreaking insights into the atmospheric characteristics and chemical processes of potentially life-supporting worlds, setting the stage for an era of exoplanet exploration at an unprecedented level of detail. These advancements underscore the potential for finding biosignatures and refining the search for life beyond our solar system. Are we on the brink of a cosmic revelation? With the JWST and future technologies, humanity is closer than ever to answering one of our oldest questions: are we alone in the universe? The mysterious lights on Proxima Centauri b may hold clues that could reshape our understanding of life and intelligence beyond Earth. As we continue studying Proxima b, the TRAPPIST-1 system, and countless other planets, we edge closer to unlocking the mysteries of the cosmos. What do you think is out there? Are the lights on Proxima Centauri b signs of an advanced civilization, or do they have a more natural explanation? Share your thoughts and theories, and stay tuned as we explore the remarkable discoveries from the James Webb Space Telescope.